Okay, so welcome guys to another video. Yeah. Okay, so I've been uploading for a while and I just thought that okay, I should upload something, and this is something I did like a thought experiment on recently. Just read it somewhere in a book and well, proving it, you know. Okay. So our task is to prove that there is always an irrational number between 0 and x such that x is an element of the real numbers. So yeah, I guess if you don't know, the real numbers are divided into two parts, the irrational numbers and the rational numbers. Wait, no, that's not how you write them. That's how you write them. Okay, the rational numbers, yeah. So yeah, that's basically the bigger thing that we're going to be using today, right? Okay, so I'll rub this off. Okay, so we start by dividing it up in cases, right? So case 1, x is an element of the irrational numbers, right? Okay, so basically that's like x is an irrational number. So to prove that between 0 and x, between 0 and any irrational numbers, any irrational number, there's always an irrational number. So of course, from this, so we can say that x upon 2 is also an element of the irrationals, if this is true, right? Because well, it should be obvious, but okay, since 2 is not an irrational number, neither is it 0. Yeah, I think for like every irrational number, okay, so any irrational number times a rational number, so this is basically x times 1 upon 2, right? So any irrational numbers times a rational number that's not equal to 0 is irrational. Yeah, I think that's like, yeah, I'm pretty sure that's true. Okay, so anyways, moving on. So we've got this relation now. We've proved that there's one in between these, but well, what do we know? So just to be sure that there's always one between any two numbers, we're going to take the arithmetic mean of these two, right? So the am, if you did not know, of a and b is written as a plus b upon 2, right? So what we're going to do is take the am of x and x upon 2. So yeah, this will be x plus x upon 2 upon 2. Of course, this is like really simple to simplify, I guess. Yeah, 2x plus x, that's 3x upon 2 upon 2. That's gonna be 3x upon 4, right? And of course, it's easy enough to show that 3 upon 4 is a rational number, right? Because 3 and 4 are co-prime integers. So, and that's multiplied with an irrational number. So therefore, we know that it's an element of the irrationals. And of course, the arithmetic mean is always in between. Okay, let me just write that now, like explicitly. So it's always in between, assuming a is less than b, less than or equal to, yeah. So keep that relation in mind, and therefore this is in between x upon 2 and x. Okay, that's pretty cool. So that's our first case. I don't know if we can fit it here, but I'm gonna just, oh, and of course, yeah, so I should always, I forgot to tell this, yeah. So remember that. Okay, so since we've got this number now from here we can take the am of say x and 3x upon 4, and then the process goes on, right? So we just have infinitely many irrationals between these two irrationals, right? Okay, that's cool. So okay, I've showed that. Anyways, yeah, so from here, now we do our case 2. So we've showed that there always is an irrational number between 0 and some irrational number. Now let's show that for a rational number, and then we can call it a day, right? Because then we know that it's true for all real numbers. Okay, so x is an element of the rationals, right? Yeah. Okay, so from here, okay, so you may wonder, how do we get an irrational number from here? Well, okay, so first of all, you know what, I'm going to leave this as an exercise to the reader. It's not that tough to prove that root 2 is irrational. It's like something you do in like sophomore year, if I'm not wrong. Yeah, sophomore year. It's not that tough. Yeah, Basically, since root 2 is an element of the irrational numbers, right? So, and of course, root 2 is also greater than 1. We know that, right? So, x upon root 2 is an element of the irrational numbers. That's the first thing. The second thing is x upon root 2 is less than x. Now we know that because, okay, so if we divide both sides by x and x is not 0, right, in this case. Yeah, I'm just assuming that's true because then these numbers are just equal. Okay, anyways, so if we divide both sides by x, we get 1 is less than root 2, which is exactly this thing. So yeah, these two relations are important. So okay, now what we do is maybe I should take the geometric mean here. Well, I guess we'll see. Or maybe just okay. Well, I guess we'll see from the geometric mean, right? So we'll take the GM. Okay, so the geometric mean of two numbers is defined as square root of the first number times the second number, right? And of course, again, for a is less than equal to b, then equal to no wait, yeah, GM of AB is less than equal to b. Yep. So that relation still holds. It's kind of like the AM. And of course, yeah, just as like a side note, maybe the arithmetic mean of two numbers is always greater than or equal to, I think, geometric mean. Yep. Or maybe it's strictly greater than, I can't remember. So I guess that's like, yeah, maybe just check that. I think it's greater than or equal to, but yeah. Anyways, so from here we take the GM of x, and okay, let's see, x and x by root 2, right? Okay, so these numbers are square root of x times x upon root 2. Now we just simplify, right? So it's x square root of x square upon root 2. Now we can just take the square root, so we get x upon the fourth root of 2, right? So so what I've just shown is that this number, the GM of these two numbers is equal to this number. And of course, what we have to prove is that this number is irrational, because then we can just go back to this cyclic process and we can repeat it, right? And we can just take the GM of this and x, and we have like infinitely many irrational numbers in between those two numbers, right? And I think like, okay, you don't have to take like 0 in x, you can take like any number in any other number. So okay, anyways, that's easy enough to prove, right? So what you have to prove is that this number is an element of the irrational, which is I wrote that like really weirdly. Anyways, I hope you understand that. So for x upon fourth root of 2 to be an element of the irrationals, right? Since x is a rational number, we'll have to prove that the fourth root of 2 is an element of the irrational. So I'm just going to show how to prove this, right? It's not that tough, but it's going to do it. Okay, so anyways, so we start by, I'm just going to put this in a box. Okay, so we start by, suppose the fourth root of 2 is an element of the rational numbers, right? You know, so we do this by way of contradiction. So anyways, moving on, right? So for any rational number, we have the rational number is equal to a upon b, such that b is not equal to 0, right? A and b are co-prime integers. That's the definition of rational numbers, if you remember that. Co-prime integers. Okay, anyways, and being co-prime just means that the GCD of a and b is 1. If you did not know that, if you know GCD, then you probably know what co-prime is, but just as a reminder, I guess. Okay. So anyways, from that, Now what we do is, okay, I'm gonna do it here, right? Yeah, do it here. So from here we do 2 is equal to a to the fourth. Okay, I guess 2b to the fourth is equal to a to the fourth, right? So from here, because b to the fourth is an integer, we just define them like that. So we can say that 2 divides a to the fourth, which implies that 2 divides a, right? Because if a to the fourth has a factor of 2, then, well, a must also have a factor of 2, okay. So we've proven that. So, okay, because that's true, so that means that we can write a as some 2c, right? Now we take the fourth power on both sides, and we've got 16c to the fourth, right? Yeah, that's 2 to the fourth times c to the fourth. So now we plug this back in here, and we get 2b to the fourth is equal to 16c to the fourth, if I'm not wrong. Let's just see. Yes, that's true. Okay, so now we divide both sides by 2, because we know that 2 is not equal to 0. Yeah, hopefully you know that. Okay, so b to the fourth is equal to 8c to the fourth. Well, this implies that 8 divides b to the fourth, but of course 8 is a multiple of 2, so this implies that 2 divides b to the fourth, but of course this indeed implies that 2 divides b. And see, look at these two. Yeah, this implies that a and b, okay, let me just name these things, 1 and 2, right? Yeah, 1 and 2. So from 1 and 2, by 1 and 2, GCD of a and b is greater than or equal to 2, right? So it can be greater than that, but for all we know, the least value it can have is 2. And of course that's a clear contradiction. So, pretty much what we've contradicted is this statement right here. So yeah, basically we've proven that this is an irrational number, the fourth root of 2, and therefore x upon the fourth root of 2 is an element of the irrational numbers, which means that we can repeat this process cyclically and again take the gm and ... I'm just going to do that, and hopefully, yeah, that is clear. So that's maybe a big QED here, QED. Okay, so that's quite, it's not an extensive proof, but it's a proof of a rather trivial thing, right? And proving trivial things is kind of fun sometimes. Doing dumb stuff is sometimes fun. So anyways, I hope you enjoyed that. Hope you learned something from that. Yeah, well, pretty nice. Yeah, also sorry I haven't been uploading for a while now. Yeah, I've kind of been busy. Yeah, you could say that. Exams and stuff. Anyways, I'll be trying to upload more, right? Yeah. Okay, thanks for watching. Bye.